Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to waves and oscillations. And so far in this whole waves and oscillations subject, we have discussed the basic things related to simple harmonic motion. Okay. The previous video we discussed the general displacement equation of SHM. So I would request you to please watch all the videos, I think 6 or 7 videos which I have uploaded previously related to waves and oscillations by checking the playlist, and then watch this video so that you understand it in a better way. So now in this video we are going to discuss some important parameters or the characteristics of simple harmonic motion. So we know simple harmonic motion is basically a kind of oscillatory motion which involves a to and fro movement of an object or a particle about a mean position or equilibrium position or center position. Okay, so in order to explain it, we can say that, let us say we have a particle or body initially at point O, and it undergoes movement in between these two extreme points P and Q, first from O to P, then from P to Q, then from O to P again, then P to Q, then O to P, P to Q, O, like that. And these 2 points P and Q, they are at the same distance from this equilibrium or mean position. So this movement which this particle is undergoing, that is called as simple harmonic motion. So the basic examples of SHM also we just discussed briefly, that is the movement of a spring attached with a mass, or a pendulum, simple pendulum, like that. There are many other examples which we will discuss. And also we discussed that the displacement, the instantaneous displacement, that is the distance of the point from the mean position with respect to time, that follows a sine or cosine curve. So here we will discuss the various things related to it: the displacement, the amplitude, the time period, the frequency, the velocity, acceleration, everything. And another important thing which we also discussed, which is the correlation between uniform circular motion, that is the movement of a particle around a circle along the circumference with a constant angular velocity, and how we can relate it with simple harmonic motion. So what we did is that we tracked the position of the particle on the circumference, then we draw a perpendicular from that point to the diameter of the circle in this way, and where the perpendicular touches the diameter, we measured that position from the center, and that position changes as the position of the particle on the circumference changes, and that also is a form of simple harmonic motion, because this point M, it moves to and fro about the center position or mean position O in between the two extreme points A and A dash, like this. Okay, like this. So this is also an example of SHM. So here we'll try to understand the various terms or important parameters associated with it. So first is the first characteristic of simple harmonic motion, which I have already discussed, but let us just discuss it again, that is displacement. Okay, so displacement, as I said, in simple harmonic motion is the distance of that particle at any instant from the center position. So here let's say the instantaneous position of the particle is this, here at this point, this blue position, if we call it here. So the instantaneous displacement is x1. So like that, if we want to measure the instantaneous displacement, there are various things which are important here. First thing is this angle when we correlate it with uniform circular motion and we have to determine this instantaneous position OM, then this angle is very important with respect to the position. So if it is theta, which is equal to omega t, then this angle will also be theta, alternate angle property. And then here we can say sin theta here is equal to, we know sin theta is equal to perpendicular by hypotenuse, which is OM by OP, or sin omega t is equal to OM by A, because OP is the radius of the circle, which is A, or OM, which is the instantaneous displacement, which is continuously changing, this which is the instantaneous displacement, OM can be written as A sin omega t. This is the general equation, but here we are taking into consideration that the initial starting point of the particle is from B, but most of the time it is not like that. The particle can start from any point on this reference circle. For that case, let us say that the initial starting point of the particle is, let's say, P0. In that case, this whole angle becomes this, and this angle POB, okay, this angle POOB is phi. So in that case, in order to measure the instantaneous displacement y, again the same thing we have to do, but in this case what will happen is that the total angle theta will be omega t plus phi, this omega t plus phi, this initial phase angle will get added up. This also we discussed in the previous video, the general displacement equation. So in that case it will become like this, the same thing, y a sin omega t, instead of that it will become, the instantaneous displacement will become y is equal to a sin omega t plus phi. This will be the general displacement equation. Okay, so here the another important thing which comes into play is the amplitude. Okay, when it comes after displacement, there is another important thing which is called as amplitude. So the general displacement equation, y is equal to a sin omega t plus phi. Here amplitude is the maximum displacement of the particle undergoing SHM from the equilibrium position. Okay, the maximum displacement. Now here in this case, the maximum displacement which the particle can undergo is this, let's say in between the two extreme points, it can be either OA or OA dash. Okay, OA or OA dash, and that maximum amplitude is equal to this radius of the circle, which is equal to A. Okay, so here in any kind of SHM motion, amplitude is the maximum displacement or the maximum distance between the equilibrium position and the mean position and the instantaneous position of the particle. In this case it is A, y is equal to A. Or we can say that when this sin omega t plus phi, sin omega t plus phi will be maximum, in that case y will be maximum, y max. Okay, and this y max is equal to A because the maximum value of sin omega t or sin omega t plus phi, whatever it is 1. In that case it is y max is equal to A into 1, which is equal to A. So this is the amplitude. Okay, then after amplitude, the next important property is phase. or the phase angle. So this we have already discussed here. So again, to repeat it, again this whole concept of the initial position of the particle. Now here the general displacement equation, as I said, it is y is equal to a sine omega t, but here it is taking into the given that the particle is starting, the original position is from B, but in case the initial position is somewhere other than B, let's say in between, in the first quadrant or the second quadrant or the third quadrant or in the fourth quadrant, whatever it is, wherever it is, it will cause a change in the, or a modification in the displacement equation. So that angle with respect to the initial position of the particle, that is called as the phase angle phi. Okay, that is called as the initial phase angle phi. Okay, and that gives us information about the initial position of the particle. And because of this initial phase angle, the general displacement equation of SHM, it is given as a sine omega t plus phi, and this phi can be anywhere depending on the position of the particle on the reference circle. For example, here it is in the first quadrant in between 0 or 90 degree, this is 0, this is 90, in anti-clockwise direction, 180 degree, this is 270, and this is 0 degree or 360 degree, whatever it is. Or we can say this is, let's say 0, this is pi by 2, this is pi, this is 3 pi by 2, and this is again 0. So depending on the position of the particle, it can be in between 0 and 90 or 0 and pi by 2 when measured in radians, or it can be in between 90 and 180 degree or pi by 2 and pi. If it is somewhere in between A and B dash, then if it is in between B dash and A dash, it will be somewhere, the value will be in between 180 degree or 270 degree and pi or 3 by 2 when measured in radians, and like that. So depending on that, the value or the position of the particle on this reference circle, the value of phi will change, and as a result this component omega t plus phi, that will also change, and that's why it is very important, and this quantity is called as phase of the motion, the simple harmonic motion. Okay. Okay, so we have covered displacement, the displacement equation, amplitude and phase. Now is velocity and acceleration. Okay, so the velocity of a particle executing SHM at any instant, it is calculated from the displacement equation. So we know, let's say we keep it simple, okay, we call it y is equal to a sine omega t. For now, let us just, for simplifying the whole thing, we just keep it as y is equal to a sine omega t. But keep in mind that it is actually omega t plus phi. But here, for making the calculation simple, we are keeping it y is equal to a sine omega t. This is displacement. Now velocity, we know, is the time rate of change of displacement, dy by dt. So it will be d by dt of a sine omega t, which is equal to a omega cos omega t, this. Or we can write it as, we can write a omega cos omega t as a omega root over of cos square omega t, or we can write it as a omega root over of 1 minus sine square omega t, because sine square omega t plus cos square omega t is equal to 1. Sine square theta plus cos square theta is 1. Or here we know that sine omega t, okay, sine omega t is equal to y by a. Okay, sin omega t, here we calculated sin omega t is equal to y by a, instantaneous displacement by amplitude. Okay, sin omega t. So here we can write it as a omega root over of 1 minus y by a whole square, or y square by a square, or we can write it as a omega root over of a square minus y square by a square, or it is a omega into a square minus y square by root over of a square is a got cancelled, so it is simply omega into a square minus y square. This. So velocity is simply velocity of SHM is equal to omega into a square minus y square. So if we want to measure or calculate the velocity values, let's say at the equilibrium position or the mean position, in which the equilibrium position, center position, the instantaneous displacement is 0. So in that case velocity value is a omega, and at the extreme position, when the amplitude is plus minus a, in that case v is 0, because whatever the value is plus minus will get cancelled, the square value it will become like that, and a square minus a square it will be 0. So this is the velocity of SHM and the general expression, and at different points, at the extreme points and the equilibrium position. So we have determined velocity. Now is acceleration. So here again, in order to find acceleration, again for acceleration, again we have to take the acceleration, again the general displacement equation of SHM, which is equal to a sin omega t. Velocity of SHM is equal to a omega cos omega t. Now acceleration of SHM is the time rate of change of velocity, that is dvSHM by dt, okay, and which is equal to d by dt of a omega cos omega t, okay, this, and again that will be equal to minus a omega square sin omega t, this, because derivative of cos is minus sin, and again because of this chain rule omega t, it will become omega, this constant will go outside. So this is the acceleration of SHM, the general expression, this. Now the general equation of SHM is a sin omega t. So here we can write it as a SHM is equal to minus omega square a sin omega t, or it is minus omega square y SHM. Focus on this part, which is this y SHM. So a SHM acceleration of simple harmonic motion is this form. Again, at the different points at the equilibrium position, the acceleration value, equilibrium position, when SHM is 0, the acceleration value will be 0, and at the extreme position where the value is it can be plus or minus a, in that case it will simply be SHM, but generally it is taken as a, so it will be minus omega square a, like that. Okay, so this is the velocity and acceleration for simple harmonic motion. Next is time period and frequency. So we know that the time period of simple harmonic motion is the time taken to complete one vibration or one complete cycle. Okay, one complete cycle, or we can say one complete circular motion, which gives us one complete cycle of simple harmonic motion, that is from O to P, P to Q, then back to O. When it reaches again the center or equilibrium or mean position, that is called as one complete cycle or one vibration. So the time taken to do that is called as the time period of simple harmonic motion, and frequency of SHM is the number of such complete vibrations in 1 second. So time period is generally given by time period of SHM is 2 pi by omega, and frequency we all know it is 1 by or the reciprocal of time period. Okay, now we know that acceleration is equal to, we just derived, it is omega square y SHM, this, or we can say that omega is equal to root over of a acceleration by y SHM, this. So by that, if putting this value of omega here, okay, we'll get time period is equal to, time period of SHM is equal to 2 pi root over y SHM instantaneous displacement divided by acceleration. Okay, and FSHM, frequency SHM, the frequency of SHM is just the reciprocal of that is 1 by 2 pi acceleration by instantaneous displacement, this. Okay, so this is the important parameters associated with simple harmonic motion. Okay, so first displacement and the displacement equation, then amplitude, then phase angle, then velocity and acceleration, then time period and frequency. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.